All right, so we were just discussing low Z nuclei. So basically you have a small number of protons, and so think about it. You have a small number of protons, so they are repelling each other, but the electrical force is much weaker than the strong nuclear force. So with a small number of protons, the electrical repulsion is really nothing compared to the strong nuclear force attraction, and that's why we could ignore, right? We didn't have any repulsion here. Okay, so that's great. So it works for low Z. Well, how about high Z, right? So for high Z, sorry, you can't ignore that electrical repulsion anymore. So as I said before, the attractive nuclear force is negative, but then the positive repulsion, the repulsive force is positive, so this gets booted up, right? So there it is, okay? So what do you notice? What do you notice? Well, the neutron's well is much deeper than the proton's well, right? Okay. But you also notice that the heights are pretty much the same, right? These are all the different energy levels. And so the heights are pretty much the same. And look what else. Since this is deeper than this, there's many more levels for the neutrons than there are for the protons, right? Okay, so how do you explain that? Well, these levels basically have to be the same. Because if they weren't the same, you'd have beta minus and beta plus decays all the time, right? Because that's how you go from one to the other, beta plus, beta minus, all right? Okay, what else? Let's interpret. This is large Z, right? Lots of protons, lots of repulsive forces due to the protons. And we're saying there's many more neutron states than protons. In other words, there's many more neutrons than protons. Well, where have we heard that before? Yeah, I just said that. All right, ta-da, right? This is the N equals Z line. The neutron number is the proton number. But where do you actually see? What do you actually see? You see that the stable nuclei have many more neutrons than protons, which we discussed before. So that's not a big shock. Okay, so there you go. So that, again, that is the nuclear shell model. And it's a huge improvement over that infinite well that we had in chapter 40. All right, enough of that. Let's talk about some applications of radioactivity. So if you're going to work in a nuclear medicine facility, or you're going to be a doctor, or you're going to work in a lab where you're using radioisotopes for tracers, or who knows what. There's all sorts of applications, so you want to pay attention. Okay, so let's start off with medicine. So radioactivity is used for therapeutic uses. That means you're not diagnosing a problem. You already know there's a problem. You're trying to fix the problem, right? Therapy. So here's a big giant therapy unit. Okay, this is something. This is called a gamma knife. So let me talk about the gamma knife because it's kind of cool. All right, so if you just have, let's say you have like an electron beam therapy. So let's say there's a tumor right there. So if you shoot a beam of high energy electrons, you're going to kill the tumor, but you may also kill some cells along here and along here, right? So it's not, it's good because you're killing the tumor, but you're kind of doing some collateral damage. All right, so people thought, well, gee, how could we fix that? So they came up with a name. So gamma knife. It's a great name, gamma knife. So gamma knife, instead of using one high energy beam, and they don't use, so that I was talking about electrons, or whatever, I don't care. This didn't have to be electrons, it could be anything, but it was a one high energy beam, has collateral damage. So what they do this here, they have like 200 incredibly weak beams, but they all intersect where the tumor is. So that's called the gamma knife. And they use cobalt-60, which is a gamma emitter. So Yeah, all right. And there's actually one of these things in Honolulu, a gamma knife. So they basically use these things primarily for inoperable brain tumors. If you can't operate, you got to do something, right? And so there it is. Pretty cool, gamma knife. Okay, they also use radioactivity for diagnostic purposes. They can study the function, and they can see if parts of the body are not functioning properly, all sorts of things. So nuclear medicine, that's kind of cool, huh? Like children's hospital, and nuclear medicine. There's lots and lots of uses in industry, and I talked about that at the very beginning. Now, let's talk about something that's very important if you're ever going to do anything with this. So we want to talk about external exposure versus contamination. Yeah, so if you want to make a lot of money and you want to be a pharmacist, you should think of becoming a nuclear pharmacist. So those are the people who come up with the radioactive drugs. And like I say, you know, most scans are scheduled in the morning, and so the nuclear pharmacists have to work at, you know, middle of the night or early morning or something like that. But they make tons of money because there's not many people that do it, you know. And anyway. All right, let's talk about external contamination versus, external exposure versus contamination. All right, so here's external exposure. So this thing is called a sealed source. So a cobalt-60 sealed source. So in your gamma knife, you have, you have 200 sealed sources, and they make them so the beam comes out at a certain direction. And like I say, so you just aim all the beams at the tumor, right? But here's the thing: it's a sealed source, right? So I mean, the cobalt-60 this is like a doubly encapsulated stainless steel thing. So the cobalt-60, the radioactive cobalt-60, is inside this. So all right, this thing is emitting gammas. You know, the gammas penetrate the stainless steel like nothing. You know, so all I'm saying is you're never going to touch the actual radioactive material. You're going to get exposed to the gammas, which is, you know, dangerous and everything, but you're never going to get the radioactive material on your body. You're just going to get nailed by the gamma rays. All right? So in other words, since you never touch the radioactive material, you don't become radioactive. You're exposed, right? You have external exposure to the high energy gamma rays, but you never become radioactive. On the other hand, let's talk about I-131 therapy. So this is iodine. So iodine naturally is taken up by the thyroid. So people have thyroid cancer. They usually remove the thyroid, but then you don't know if you got everything, right? So then they usually give you I-131 therapy. So basically what I-131 therapy is, you actually ingest I-131. So you're ingesting radioactive material, all right? So you are contaminated, right? You have radioactive material inside your body, you know what I mean? So it's not a sealed source. I mean, you know, it's in you, right? So you're contaminated. So what does that really, really mean? Well, this is what it means. Think about it. You're in a hospital room, right? You've been taking I-131, whatever form, liquids usually. And so that means when you sweat, guess what? Your sweat is radioactive. When you go to the bathroom, guess what? Your excretory material is radioactive. Yeah, you get it? So here's the room, right? So they have to prepare these rooms when they do I-131 therapy. So you can see that they wrap everything to death, right? You know, disposable utensils, everything is wrapped. The doorknobs are wrapped. I mean, they got to be super, super careful. Nobody's allowed in there except for maybe, you know, somebody who's fully clothed, and then they throw the clothing away and stuff. But this is a big deal, this I-131 therapy. And then after the patient is done with it, it has a short half-life, and so after the patient is done, then, you know, they got to throw all, they got to dispose, they have to store all this stuff, because, you know, it could be radioactive. So they got to store all this stuff, you know, all these covers and everything. Then they got to completely wipe the room down. It's an incredible amount of work, you know. After they wipe it all down, then they got to test it, you know, like with some kind of radioactive measuring device. I mean, it's a huge amount of work. So you can imagine it must be pretty expensive too, right? Okay. And it's the same thing if you work in a lab, right? If you're working in a lab, you have radioactive material, you know, you clean it up as best you can, and then that's not good enough. Then you got to test it. So there's all sorts of different ways of testing it. Like they have something called a wipe test. You take a certain piece of, like, sort of like gauze material, and you just wipe around where you were using it. Then you put it on a radiation detector. If it's clean, it's clean. If it's not, you go back and clean it up. So it's a lot of work. Okay, let's talk about the biological effects of radioactivity. This is what we are concerned about, right? Okay, so remember, this is ionizing radiation. It's not this wimpy chemistry, you know. This is nuclear physics, right? MeV energies. So radiation causes ionizations of atoms, which will affect molecules, which may affect cells, which may affect tissues, which may affect organs, which may affect the whole body. So there you go, all right? Now, the biological effects, they really depend on how much radiation energy is absorbed by the tissue, right? So how much energy is absorbed by the tissue, and then how the tissue reacts to that radiation. Now, they have some weird units, but whatever, you know. Okay, so the dose in gray is the energy absorbed by 1 kilogram of tissue, okay? So get rid of that. All right, so the dose in gray is energy per kilogram. So 1 joule per 1 kilogram, all right? It's the energy absorbed by 1 kilogram of tissue. Now, you know, different types of radiation have different biological effects. You know, I mean, gamma does certain things that alpha don't, and so forth and so on. So they got to take that into account too. So this is called the relative biological effectiveness of radiation, RBE, right? And so the larger the number, the more dangerous. So alpha particles are 20 times as bad as X-rays. I mean, there's other factors, hold on, all right? But this just says that, you know, that these do much more damage than these or something like that, right? Okay. All right. So what's important? What's important is the dose, right? How much energy there is and what type of radiation. So there's both factors. Okay, so how do you include both of those? So to include both of them, you have to use what's called the dose equivalent. So the dose equivalent combines the dose, which is the energy, and the RBE, right? So the dose equivalent, which is in sieverts, right? Sieverts, okay? That's the energy absorbed, which is the number of, so it's the dose in gray, multiplied by the RBE, all right? Now, there's something that may drive you crazy. You know, in physics, you know, you usually look at the units as an algebraic quantity, right? And everything works out great. Well, here's a situation where it doesn't work. See, the RBE has no units. So the dose is in grays. The dose equivalence is in sieverts. Now, that's insane. I mean, if you're, you know, used to what we've done in the past, right? Because a sievert equals a gray times a number. So, you know, so you would think, well, unit-wise, a gray is a sievert. But don't say that, right? Don't say that. I mean, you have to remember the dose, which is just the energy, is in gray. When you include the RBE, which is what you want to do, right? That's the dose equivalent in sieverts, okay? So you just have to remember that. It's not like, you know, our usual units. Sorry. I mean, what can I say? Okay. So the dose is in grays, dose equivalents in sieverts. Yeah, the units, sieverts and grays don't work as algebraic quantities. Sieverts is always the dose equivalent. Gray is always the dose. RBE is just a number. So this is the first time you've probably seen it, probably the last time, but it just doesn't work like it usually does. All right, let's do an example. And these are the metric system units, I guess, or the modern units. There's old-fashioned units, I'm not even going to talk about them. So nowadays people talk about grays and sieverts. In the olden days they talk about rem and rad, and we don't care about it. All right, so suppose a 90 kilogram radiation worker accidentally receives a whole body exposure of 2,000 millisieverts from a proton source. How much, now here they want to know how much energy is actually absorbed by the worker's body. Okay, now look, here's the thing. This is a hint, all right? Or this is what you would look up. I mean, you wouldn't see these two sentences in the problem. As soon as you see 2,000 millisieverts, you say dose equivalent, all right? Dose equivalent. All right. And then, since it has a dose equivalent, and you want to find out the energy, you know, the dose equivalent includes the RBE, so you got to look up the RBE, right? So you'd have to look that up, or they'd have to give it to you. Okay, so we know that the dose equivalent, whatever, equals a dose times RBE. So therefore, the dose, right, the dose is the energy. The dose equals the dose equivalent divided by the RBE. That's all. So we just have, okay, what's the dose equivalent? 2,000 milli, well that's 2, right? So it's 2 sieverts. And the RBE is 5. So normally we would say this is, you know, 0.4, right? We would say 0.4 sieverts, but that's wrong, right? It's 0.4 gray. 0.4 gray. Right? 0.4 gray. Okay, so that's you know, energy per kilogram, right? That's energy per kilogram. But this is a 90 kilogram guy. So now we have to say that the absorbed energy is equal to the 90 kilograms and 0.4 grays. You know, again, what's a gray? So it's 0.4 gray, but a gray is a joule per kilogram, right? A gray is a joule per kilogram. We have 0.4 gram. So then, so this, I mean, yeah, units work here, right? Units work here. So we get 36 joules. So the guy absorbed 36 joules of radiation energy. Now, of course, we want to know, well, is that going to kill him or what, right? We're going to talk about that. Okay, so here's some numbers for you. Radiation exposure and effects. So, now notice this is millisieverts, so they've already taken the RBE into effect, right? That's right, dose equivalent, okay, dose equivalent. So fatal dose, if received over a short period, 10,000 millisieverts. Dose resulting in 50% fatalities, 5,000. Onset of radiation poisoning, 500. Astronauts in International Space Station, 150 per year. Okay, allowable dose for radiation workers, 50 per year. Whole body X-ray scan. Most of us don't get a, you know, if you get a, most of you get this like a localized X-ray, but this is whole body. 10. PET scan, remember we talked about that, 7. Mammogram, 0.7. Chest X-ray, 0.3. Transatlantic airplane flight, 0.05. Dental X-ray. So there you go. Okay, so let's say that one of these days you become a radiation worker, maybe in a hospital or in a lab or who knows what. So what you want to do to protect yourself is you want to reduce the exposure, right? You want to reduce the exposure. So how do you do that? Well, so if you ever become a radiation worker, you will memorize this. Time distance shielding. Time distance shielding. Okay, so let's go through that. So basically, how do you reduce the exposure? By not spending a lot of time near the radioactive isotope, right? So for example, let's say your grandmother was in the hospital and she had a radioactive implant in a uterus or something like that. And so if you want to go visit grandma, you know, they say you're only allowed to be there a certain number of time, a number of minutes. So you're restricted. And that's how it is. Okay, distance. Remember, it's a point source, right? Right? And the intensity goes as 1 over r squared. And so the exposure is 1 divided by the distance squared. So if grandma was right here, you know, let's say you were here, then you double the distance, then the exposure goes down by a factor of 4, right? 2 squared is 4. So all right? So basically what they do in the hospital, if grandma's over there, they have a place marked off on the floor and they say, thou shalt not cross that line, because they're trying to have a lot of distance. And the third thing they do is shielding. So, you know, look at it. If grandma has a radioactive implant, she's radioactive. And of course, if you come near her, you know, you're getting exposed, right? You're not getting contaminated, but you're getting that external exposure, right? And so what they do, they use shielding. They put something between you and grandma to block the radioactivity. So look at this. So see, this absorbs the radiation, all right, or most of it anyway. So that's shielding. Okay, if you work in a lab, you know, you might be working with like a little beta emitter, but you do it behind this little shield thing. All right, so that's basically it. Oh, here. All right, so this is called a hot cell, and this is, you know, probably like steel or lead or something like that. So they usually make like radioactive isotopes inside that. So it's incredibly radioactive inside it. That's where they make cobalt-60, for example, the sealed sources. So you have gobs and gobs of lead and steel shielding, so you protect the workers. All right, so basically what is again? Time distance shielding. You want to minimize the time, want to maximize the distance, and you certainly want to use proper shielding. But you're going to use proper shielding, right? You're going to, okay. All right, this is sort of extra, but it's fun. So people that are statisticians, sometimes they do something called quantitative risk assessment. So they figure out risks. Like life insurance companies want this kind of information, right? To live is to risk. There's a risk in drinking a cup of coffee. There's a risk in going out of the house, right? You know, right? I mean, some nutcase could hit you or whatnot, right? There's a risk of not going out of the house, like if you're breathing radon. You don't have that in Hawaii, but you have it on the mainland for sure. So there's risk associated with everything we do. Everybody knows that. Okay, so this is something that people have figured out just by statistical analysis, you know. So the risks of daily life, activities carrying an average risk of death of 1 part per million, all right? So so all of these are exactly the same. So these things, you know, they carry an average risk of death of 1 part per million. So let's just look at a couple things, right? So one chest x-ray, that's the same thing as traveling cross-country by jet, living 1 week in a building because of radon, that's on the mainland, living 5 weeks outdoors because of outdoor radon, living in Denver because cosmic radiation is, you know, Denver's high elevation, living 5 years to a nuclear plant, living 50 years within 8 kilometers of a nuclear plant. Or look at this. If you have friends not living the word of wisdom, look at this. Smoking 1.4 cigarettes. That's the same as, well, again, it has the same risk. Living too much with a smoker, diet soda, peanut butter, peanut butter, liver cancer from whatever that is, right? Eating 100 charcoal broiled steaks. Okay, that's travel. Okay, motorcycle, 5 kilometers, 16 kilometers bike, 50 kilometers car, 1300 by train, 1600 by airplane, on and on and on. And then working in a coal mine, not a good thing, right? Living in New York City or Boston, air pollution. So all of these have exactly the same risk. 1 part per million death. So I just thought it was kind of fun. All right. Oh yeah, now I got something extra for you. This is not in the book, but this is fun. So you can turn it off if you want to, but this is fun. Oh, what if I know what it is? Okay, the solar neutrino problem. All right, so how do people study stars? Well, so the theoretical astrophysicists, they come up with models, right? And so this is the model, okay? And so the model is that you have this nuclear fusion where 4 protons fuse and you get helium out of it with gamma rays and neutrinos and da-da-da-da-da, right? So the theoretical type, they come up with these models of what happens inside a star. Well, whoopee, you have a model. You got to test it, right? So then the experimentalists, they set up an experiment. So for example, if this model, it predicts that there's going to be neutrinos, right? Electron neutrinos, that's important, all right? Remember that. So the model says there's going to be a certain number of electron neutrinos emitted every time this reaction occurs. Okay, so then, people know that neutrinos, they go all the way from the sun to the earth. They don't, they don't get absorbed very, very often in the atmosphere, hardly ever, in fact. And so basically, you can calculate how many neutrinos will hit the earth. Okay. And so what you do is you build a detector, and you want to detect, you want to count neutrinos, and you want to see if it agrees with your model, all right? Okay, so observations of solar neutrinos coming from the sun, tell us what's happening in the sun's core. All right, so, so in the 60s and later, people built these gigantic detectors under the ground, and they built them under the ground because the neutrino will penetrate the ground. Most other things won't, because you don't want to get false, you don't want to get false results, right? So you want to shield out everything else that will cause a hit in your detector. So you build them way underneath the ground, so only the neutrinos are going to go, reach the detector. So here's an example: Home State Gold Mine, South Dakota, USA. So it's an abandoned mine. So they built this big tank, 400,000 liters of pure dry cleaning fluid. So when the neutrino hits it, there's a reaction. And they can measure it, and they can use that to count the number of neutrinos. Okay? So again, all they're trying to do is verify the theory. All right, so here's the thing. So the theory, so this is just an example. So let's say the theory predicts that, let's just say a day. I'm just making this up, all right? But you'll get the idea. Let's say the theory predicts that every day 6 electron neutrinos will hit the detector in South Dakota, okay? Well, so that's the theory. So they built this detector. They took data for years and years and years, and all they ever measured were 2 per day. Then other people built detectors, and they got the same result. They're supposed to measure 6, they get 2. So they were always off by a third. I mean, they only measured 1/3 of what they were supposed to measure. So this was kind of a problem, because different experiments had the same results, and they disagreed with the theory. So you had a situation where the experimenters were saying, well, you dumb theorists, your theory's wrong, fix your theory. And the theorists would say, my theory's right, you dumb experimenters. I'm exaggerating, but you know what I mean. So this became known as the solar neutrino problem. And it existed for years and years and years. I mean, people going over their calculations, people going over their experimental results, no resolution. More and more experimenters getting the same result, no resolution. What a pain. So then, somebody came up with this crazy idea. Now remember, the solar model predicts that electron neutrinos are emitted from the sun. So all the detectors that people built were designed to detect electron neutrinos. No kidding. Well, so everybody knows, or at the time everybody knew, there were three kinds of neutrinos: electron neutrino, muon neutrino, and tau neutrino. Everybody knew that. So I don't remember the name of the guy or girl, whatever it was, person, but whoever came up with this idea said, well, maybe, just maybe, these electron neutrinos, right, these electron neutrinos, just maybe when they're flying from the sun to the earth, maybe they're changing. So maybe some of them are becoming muon neutrinos, and some of them are becoming tau neutrinos. And so in other words, if you start off with 6 electron neutrinos, by the time they get to the earth, there's 2 muon, 2 electron, and 2 tau. Now that sounds like, come on, give me a break, right? But think about it now. Like neutrons decaying into protons, protons decaying into neutrons. I mean, this whole decay thing happens all the time, right? And so, I mean, it sounded like, come on, it sounded like somebody just making up something to get the nice result. But hey, there's history, right? I mean, things decay. So people said, all right, maybe it's true. So then what people did, they built detectors that not only would detect electron neutrinos, but they'd also detect muon neutrinos and tau neutrinos. All right, here's one example. This is in Canada. Sudbury Neutrino Observatory, 1,000 tons of pure water. So it's under the ground, Here's one in Japan. Super Kamiokande, I don't know if I pronounced that right. So basically everybody calls this Super K because nobody wants to pronounce that right. So Super K, 50,000 tons of pure water. These things are photomultiplier tubes. Remember we talked about photomultiplier tubes? When we talked about you can detect single photons? So they have this gigantic spherical cavity. It's all full of these photomultiplier tubes. And it's usually full of water, but sometimes they have to clean, the photomultiplier tube, so they have to let some of the water out. Then these people get in the raft and they clean it. Or, maybe if something doesn't work, they have to fix it, whatever. All right, so anyway, so now you started having all these experiments that could detect all 3 neutrinos. And guess what? The theory said 6 were produced. The detectors detected 6. So no longer solar neutrino problem. Yay! All right. Now here's, okay. By the way, I don't remember what year, but I think it was in the 1990s. So they were cleaning the photomultiplier tubes, and something went wrong. And so I think 2/3 of the photomultiplier tubes broke. Total disaster, right? Total disaster. I mean, this incredibly famous experiment, all of a sudden, bang, right? And so, this was in Japan, and so the Japanese government, they just paid for new tubes, like $7 million. And this is like in the 90s. So that was pretty nice of them, right? But anyway. Okay, so let's just review. So we talked about the size and structure of the nucleus. We talked about the nuclear strong force. We talked about the simple shell model. We discussed radioactive decay, half-lives, and biological applications and radiation dose. So this is the modern atom. Electrons constant motion around nucleus. Inside the nucleus, the protons and neutrons jiggle, move around, and the quarks move around inside the protons and the neutrons. And don't forget, if you drew the atom to scale, you made protons and neutrons a centimeter in diameter, electrons and quarks less than the diameter of a hair, the atom's diameter greater than 30 football fields. So most of an atom's volume is empty space, which is kind of cool. Then we learned about isotopes, right? All carbon has 6 protons, but every isotope has a different number of neutrons. Still carbon, but it will have very, very different nuclear properties. I mean, look at, different half-lives, all sorts of different things. So different nuclear properties. This was the weird thing, right? The mass of the separated nucleons was greater than the mass of the nucleus itself. And that, we had to use this to explain that. If you want to calculate the binding energy, well, we learn how to use it, right? We learn how to use this formula with our appendix C, okay? Just calculate the binding energy. Yeah, I keep talking about this, right? If this is a spontaneous decay, this mass has to be greater than this mass because some of the mass was converted into energy. So the mass of the helium is smaller than the mass of the 4 protons. And that's just because of E equals mc squared. Mass per nuclear particle. Hydrogen has a lot of mass per nuclear particle, so it will fuse to get, all right, to release energy. So this is fusion when you're fusing together. This is fission when you're busting apart. And then, of course, iron is the last, right? It's the last thing here. So iron cannot fission or fusion. And that was important because of the neutron stars and the black holes, remember? When the iron core of the star becomes, when the core of the star becomes iron, there's no longer any way to produce energy, so the star collapses. And then radioactivity, it's spontaneous, it's random. You can never say which nuclei will decay. You can only say if you have a whole bunch of them, half of them, but you can't say which ones. Energy is released in this dangerous ionizing radiation, millions of electron volts. And, oh yeah, right? So I think this is the easiest. This is one that most people use. The number of radioactive nuclei remaining equals the number you start with times 1/2 time divided by half-life. So this is the same thing as this, but it's just easier, you know? And then when you have a Geiger counter, what you're actually measuring is the rate, right? The rate. And so that's this equation. This is the modern unit, becquerel, decay per second. This is old-fashioned. People used to use it, Curies. Alpha decay, you spit out, alpha decay is a helium-4. So you spit out a helium-4. Okay, beta, you spit out either an electron or a positron with either a neutrino or an antineutrino. And you have to have the third particle to conserve momentum and energy. Radioactive dating. And then this is our shell model, which accounted for beta decay, right? Beta plus and beta minus. And then that with large Z, you need a lot of neutrons. And then this thing, right? Dose in gray, energy per kilogram. But then dose equivalent, you include the RBE, because some radiation is more dangerous than others. And the units are not algebraic quantities. You've got to remember that. And how do you reduce exposure to yourself? Time, distance, shielding. And then, well, that was just for fun, right? There is no longer a solar neutrino problem. Thank you very much. We're done.